Welcome, ladies and gentlemen. Continuing our exploration of substitution reactions. We have two reactions here that look almost the same, but there's subtle differences. Can we find these differences? Can I find my pen? There we go, I found it. I'm highlighting the differences here and here. There you go. So the nucleophile changed. Which nucleophile is stronger, the neutral amine or the N minus? The N minus. Much stronger nucleophile. Also, pKb 14 minus 40. Strong base plus heat is present. This is a new, that's a hashtag. I don't want a hashtag, I want H. This is what we call an override. Override. That combination, regardless of the other parts of the analysis, which you will do, never skip your 4 steps or 3 steps of an analysis with a conclusion. Never skip those. But when you see that combination on top of those, your new conclusion is this reaction here, E2. There's a lame attempt at a Shakespeare reference down there. E2. So we'll look at the E2 mechanism after the video. It's a simple mechanism where the base takes a hydrogen instead of attacking a carbon. That's different than we've seen. So let's do the analyses together as we go. Same Rx. Secondary, SN1 or 2, we don't know. Mobata. Rx secondary, SN1 or 2, we don't know. Nucleophile for the first one, blue nu. 2, nu RNH2. It's not RNH2. It's not got a minus charge, so you can't call it strong. It's not a neutral oxygen, so you can't call it weak. Well, how's that for a nice little summary of getting to a moderate nucleophile? Ah, I like that. It's not got an anion, and it's not neutral oxygen. It's neutral nitrogen or sulfur. Those two, both are moderate. Oh, don't put it in blue. Oh yeah, blue down here though. Moderate. What's your conclusion or lack of conclusion based on that matter? Moderate. Yeah, more Mubara. So we still haven't made up our mind on the top one. 2, down here, nu RNH minus, strong. Here's where I get my override in. But we've got an override that takes over. Strong normally favors SN2. I'd like you to show me you know that. Strong favors SN2, but you're overriding that decision with an E2. We don't know what E2 is yet, but we know that it's happening when we have a strong base plus heat. And then the solvent is the same in both. Acetic acid, yeah. Oh, I almost gave the answer. What category? Your 3 categories of solvent are polar protic, polar aprotic, non-polar. Which one? Polar protic, it's got an H bonded to O. I'm writing protic first, I don't know why. Polar protic, SN1, SN1 is your conclusion. Your products are as shown up here. And we got to show that we know that during an SN1, where there's a carbocation, you get 50% R, 50% S. You must acknowledge that. Well, I think you can go, that covers it, right there, 50% R/S. I like it. And this is one where it's a positive charge, but I don't have to neutralize it at the end. When did we have to neutralize a positive charge? What kind of products do we not want to put in this box? It's in the videos. It said don't put a strong acid in this box. We never finish with a strong acid. Did we finish with a strong acid this time? No. This is a very stable acid with a pKa of 10. It is a legitimate final product. You do not neutralize that ammonium there. Ooh, leaving group. This is one where the leaving group is the conjugate base of nitric acid. How do I know that? ONO2 is N with 3 O's and a minus charge. That's nitrate, correct? Nitrate is the conjugate base of nitric acid. Let's draw nitrate. You got your 3 O's. You got your 18 for oxygen. This is NO3 minus, by the way. That's my name today. NO3 minus. 5 plus 18 plus 1. Ooh. 5 plus 18 plus 1. 1924. 2, 4, 6, 8, 10, 12. And yeah, we're running out of there. Almost done. Almost done. Got to put a minus charge on each O, correct? Except for the bottom O. There you go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I got 26. Did I do some bad math? 5 plus 18 plus 1. 19, 24. I got more than 24 electrons up there. I think I'm counting well. 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I just counted wrong. Yay, we win. And yeah. Here's E2. First of all, when do we get E2? It's a new thing. We didn't have this the other day. If you have the combination of a strong base and heat, and we do, pKb less than 0, heat, triangle, bingo. Here's the mechanism as promised. Although I said I'd do it without the video, but we're doing it on the video. You got your base. Yeah, shadow mechanism. To be a strong base like that, I think there's not a single base that wouldn't have a minus charge, right? Yeah, every strong base has a negative charge. And we're going to make this mechanism fancy. H is attached to a carbon, is attached to a carbon, is attached to an LG. What's LG? Leaving group. And these other positions are here. I don't know, just call them generic R groups. R equals C or H. And RIV. And here's the mechanism. It's kind of a cool mechanism. You don't need this for your activity, by the way. It's extra. You guys love extra. Extra. And what happens with a mechanism is the base grabs this H. Why does it grab that H? Because it's in a position that's called beta. Alpha is Alpha equals C with LG. What's LG stand for again? Leaving group. What's an excellent leaving group? We have a definition. We have a definition that covers 7 leaving groups with one definition. Why was NO3 minus an excellent leaving group? We forgot. Sorry, say it again. It is the conjugate base of a specific type of acid. Strong acid. The conjugate bases of strong acids are the excellent leaving groups in this course. Nitric acid has a pKa of -5. Yes, sir. Yes, but we're not talking about base strength. We're talking about stability of the species as it leaves. So yeah, it's not about being a base now. It's about being a very stable species. And if you have H plus, a proton, attached to a very stable species, it's called a strong acid. Let's use what we already know so we can talk about what we're learning. And here we go. We've got E2. Base grabs an H from which position? Beta. What's the definition of beta? Vicinal to alpha. What's vicinal mean?
On purpose?
No, in this course it means on the adjacent position. Like vicinal halohydrin was a halogen on one carbon. On the adjacent carbon was an alcohol. Vicinal dihalides we made too, with a bromine, BR, and an alkene. We made those too. Bromine's on adjacent carbon. It's vicinal. And the base grabs the H. Can you tell me what you think happens to the old sigma bond between the beta H and the beta position carbon? Becomes a pi. Elimination always makes pi. Elimination always makes pi. Elimination. Always makes pi. And then what's the leaving group do? I just said what it does. That's all leaving groups do. They leave. And there's the pi, you see it? Gotta get our fancy pen going here. You got C, double C now. And we got just the R groups. They could be anything. And what else you got? We got the base. What happened to our base? The purple base is now the conjugate acid, right? And what else did we make? Lg with a minus. Here's your 3 species. Most important being, of course. Yeah, I don't like it. So we're ready to finish our activity finally. So we didn't really need any of that for our activity, but we can predict our products now. This is alpha. How do I know that's alpha? It's got the leaving group on it. Therefore, anything adjacent to that with an H on it can have that H removed, right? Major, minor. Oh, I wonder which one's major. Well, if you take it from the left one, here's the result. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. My apologies, didn't fit in the box. I'm gonna make it fit in the box. 1, 2, 3, 4, 5, 6. Well, tell me what's the difference between the first product and this second one? What's the difference? And why is that minor? Yes, one is cis, which suffers from more steric hindrance. And this is trans, which has no steric hindrance. That's why it's major. Yeah, this methyl group is nowhere near this propyl group. Here, this methyl group is, hey, we got a word for it when it's right in front of it. If you're looking head on, you wouldn't even see the methyl group if your eye was looking at here, because this group would be blocking it. We have a name for that. Eclipsed. Yeah, cis alkenes are permanently eclipsed, aren't they? You can't rotate away from it. And the minor would be just take the H from the far side, the terminal side. Terminal. And then we can have a brief discussion of why that is worse than the first two. 1, 2, 3, 4, 5, 6. Most minor, if you want to get even more clear. And I'll just do an oral discussion of why it's most minor. So far, we've learned a couple things about stability in terms of carbocations and radicals. They're both stabilized if there's a lot of carbons attached to the cation or the radical carbon. And we had a name for that, why that was stabilizing. Like a tertiary version of a cation is more stable than a secondary version of a different cation. Why? It has more hyperconjugation. That covers cations, radicals, because they're missing an electron too, and pi. Pi is not really missing electrons, but those electrons are kind of far out there. They're not as close to the nuclei as possible. They need help. And they get help with hyperconjugation. So which of the three alkenes has the most hyperconjugation? That translation. Which alkene has the most carbons bonded to the alkene carbon? The first two. They each have 2 carbons bonded to the alkene carbon. Right here, there's a bond to this and a bond to this. That's 2 groups. I call it di-substituted. We can do it for alkenes, but we can't use degree sign. So di-substituted plus trans is better than di-substituted, sorry about my writing, plus cis is better than mono-substituted. So hyperconjugation is the #1 factor. So the one with more groups is better. The second factor is cis versus trans. There's only a small difference in their stability. But mono versus di, that's a big difference in stability. Okay? And let's just make sure you have what's in all the boxes, and you're good to go on this one. Double.